The immunization of any individual, by developing antibodies to either natural infection or to a vaccine, results in direct protection for that individual from subsequent infection. It also results in the indirect protection to all the individuals that they might have infected. Thus, to assess the full potential impact of vaccination, one must consider both the direct benefit of vaccination to the individual and the indirect benefits of vaccination to the population. Consider the vaccination of infants, a strategy that has been employed to limit many potentially dangerous human infections like polio, measles, mumps, rubella, and whooping cough. We can then ask, what will be the impact at the population scale of immunizing some fraction p of all infants, where p is the product of the proportion of infants vaccinated and the vaccine efficacy, or the probability that a vaccinated infant will successfully develop immunity. Recall that infection removes susceptible individuals at a rate related to the basic reproductive number R0, and susceptibles are added to the population through births. Thus, immunizing a proportion p of births reduces the rate at which the susceptible population is replenished. It can be shown then that the new reproductive rate for an infection in a population where p% of individuals are immunized is R effective, which is 1 minus p times R0 in the absence of vaccination. Recall again that R effective is the expected number of new infections due to a single infection, and an epidemic is only expected to establish in a population if this number is greater than 1. So, if R effective is less than 1, then we would expect that infection would not be able to invade. Solving this relationship for p, we can calculate the critical immunization fraction needed to ensure that R effective is less than 1, which gives us p greater than 1 minus 1 over R0, which says that so long as the proportion vaccinated is greater than this quantity, an epidemic will not be able to spread. This fairly simple equation suggests a very powerful result for public health, that we can effectively prevent an infection from invading a population by immunizing less than 100% of all births. This phenomenon is referred to as herd immunity. We can see immediately that as R0 increases, the proportion of children born that we would need to vaccinate also increases, and that proportion rises rapidly at first. So for a pathogen like smallpox, with an R0 of approximately 5, we might only need to immunize 80% of children. But for pathogens like mumps or chickenpox with R0 nearer to 10, we would need to immunize 90%. And for pathogens like whooping cough and measles with R0 near 20, we would need to immunize close to 95% of all children born each year. Recall that the herd immunity threshold is the percentage that must be immunized, not just vaccinated. Pediatric vaccination with pertussis or measles vaccine generally stimulates immunity in less than 90% of infants due to interactions with maternal immunity. So infant-based vaccination strategies alone are not expected to be effective to achieve eradication of pathogens with such high transmissibility. So while herd immunity is an encouraging phenomenon, indicating that eradication may be possible even with less than perfect vaccination coverage, it also highlights the inherent challenges to eradication. Even if the critical vaccination level necessary for herd immunity is difficult to achieve, the indirect effects of vaccination will still have positive benefits. The equilibrium prevalence of infection, that is, the average proportion of the population that is infected at any given time, is expected to decrease linearly with the vaccination coverage, even when coverage is below the critical level for herd immunity. When the prevalence of infection and the proportion of the population unvaccinated drop to low levels, it is increasingly likely that transmission will fail to occur due to random chance. Thus, even if vaccination alone cannot achieve elimination, it increases the chance of local elimination due to stochastic dynamics. It's important to note that in this event, if vaccine coverage is below the level necessary to achieve herd immunity, and infection fades out locally due to stochastic dynamics, the population is susceptible to reinvasion of infection. Further, as time passes, if vaccination stays below the critical coverage level, the proportion of the population that is susceptible to infection will continue to increase, leaving the population increasingly susceptible to new outbreaks. Thus, the combination of indirect protection and stochastic dynamics can be useful to achieve disease elimination goals. But the local elimination of infection must be viewed with caution, as the absence of infection does not necessarily translate into the absence of subsequent outbreak risk.